In the previous podcast, we looked at energy and work in general with a specific look at gravitational potential energy. In this podcast, number 26, I want to look in more detail at kinetic energy and power. Now in this image here, we can see that this ball is on a slope and it's raised above the ground, so it must have gravitational potential energy given by its mass times gravitational field strength times height. But I'm holding onto the ball, so at the moment its speed is 0. Now what happens to the ball when we release it? I think you will all have guessed that the ball will roll down the slope and gain speed. When it reaches the bottom, it's actually got no height anymore, so we can say it's got no gravitational potential energy. In fact, all of that energy has been converted into kinetic energy. Here's another example where we can freely turn gravitational potential energy into kinetic energy. It's a pendulum. So if I pull the pendulum back, which is a mass on a string, I pull it back to position 1, I've given the pendulum potential energy because it's now at its highest point, it's raised above the base level. I've given it gravitational potential energy. If I let it go, it will lose the potential energy and that will be converted into kinetic energy at position 2. As it rises up again to position 3, it loses its kinetic energy, slows down and stops, and at position 3 it has no kinetic energy, but it's back to having a maximum potential energy. And here's a final example, a great example provided by the PHET folks at Colorado University. It's an applet which shows a skateboarder in a skate park. So here we are, here's the skate park. It's a very simple skate park. There's no friction in this skate park, which is pretty good. And we can see that the person is going up and down, gaining kinetic energy as they fall to the bottom, losing that kinetic energy as they go up to the top. Now I'm going to call the bottom of this skateboard ramp a position which has 0 potential energy, and I'm going to raise that dotted line there until it reaches the center of that blue dot, and that's saying that when the person gets to the bottom they have 0 potential energy. So I want to have a look at how the energy is being transferred as the skateboarder goes up and down the ramp, and this graph here will show me what's happening to the energy. At the moment it's not showing me anything because I haven't checked any of these boxes here, but we can see as the person reaches the bottom they've got 0 potential energy and they've got maximum potential energy at the ends of the track. And there's the graph, maximum potential energy at the ends and minimum in the middle. Now they convert that potential energy into kinetic energy as they fall, so because this is a frictionless skate park, we don't lose any energy, which means all of the energy should have been turned into kinetic energy when they reach the bottom. So let's take a look at that one. So here, green is kinetic energy, maximum kinetic energy is in the middle, just where the minimum kinetic energy is. And because this is a frictionless skate park, energy is going to be conserved, so we're not actually losing any energy. So the total energy should be constant. And there the greenish line at the top is showing us a constant total energy. If I check the thermal energy box, we can see that there's absolutely no thermal energy because there's no friction, there's no wasted energy through heat. If I actually go and add some friction to this skateboard park, we can see that straight away some of the energy is being dissipated as heat and the thermal energy line is going up. Eventually it will reach a value of the total energy and the skateboarder will stop. All of the energy has now been dissipated as heat. So in the previous podcast we saw that gravitational potential energy can be given by mass of an object multiplied by the gravitational field strength multiplied by its height. That's gravitational potential energy. Now we can actually derive an equation that allows us to calculate kinetic energy as well from easily measurable quantities such as an object's mass and the object's velocity or speed. Let's imagine a car about to convert energy in the fuel into kinetic energy. So it's about to do work. So here it goes. So it's speeding up, going along to the finish line, and in doing so it converted energy in the fuel into kinetic energy. So by the time it reaches the finish line, it's actually gained speed. So the engine is providing a push force, giving the car acceleration, and it's moving through a distance, let's say a distance d. How much energy is converted into kinetic energy? So in other words, how much work is done? So let's have a look. The work done by the car's engine is given by W equals Fs. Work done is force from the engine multiplied by S, the distance moved. But as we know, Newton's second law states that the force is equal to the car's mass multiplied by its acceleration. So combining these two, here we get W equals MAS. The work done is the mass times the acceleration times the distance moved. But acceleration is change in speed over time, or v minus u over t. And distance traveled is average speed times time, or v plus u divided by 2, that's the average speed, multiplied by time. In both of these cases, the car is starting at 0 speed, so we can forget the u. So we've got v over t and vt over 2 for distance, and this one for acceleration. So what we're going to do is we're going to substitute these two equations in to this equation here and see what we get. So there's our equation. Work done is equal to mass times acceleration times distance moved. So here's a first equation here which we want to substitute in. Okay, so we're going to take that, v over t, and we're going to put that right in there. And here's the second equation. I want to take that, vt over 2. I'm going to take that, substitute it in for the s, right there. This is what we get. Work done is m v times v over, and times t over 2t. Now you should be able to see that we can cancel the t's here. T divided by t is 1, and we can also stick the two v's together to make mv squared over 2, which is normally written as half mv squared. So kinetic energy is given by half mass of the moving object multiplied by the velocity of the moving object squared. So let's apply this equation to calculate the kinetic energy of this supermarine Spitfire. So we've got kinetic energy is half mv squared. So we've got 2,400 times a half, it's half of the mass, multiplied by 140 squared. So half of 2,400 is 1,200, multiplied by v squared, which is 19,600. Multiply those two things together, and we get about 23,500,000 joules of kinetic energy. A large number. Let's have a look at another example. So here's a container ship. Mass 1 times 10 to the 8 kilograms. Velocity 10 meters per second. So again, it's going to be given by the mass times a half times v squared. In this case, v is 10, so 10 squared. So that's going to equal half of the mass there is going to be 0.5 times 10 to the 8 times 10 squared, which is 100. I can do that in my head. So that is 5 times 10 to the power of 9 joules. So we have 5 times 10 to the 9 joules, that's 5 billion joules, and here we have 23 million joules, both large numbers, but the ship has a greater kinetic energy, primarily because it's got such a large mass compared to the aeroplane. Now let's move on to power. So power is defined as the rate at which energy is transferred, how quickly the energy is actually used. In terms of an equation, we've got power equals work done over time taken, or P equals W over T. Looking back at the aeroplane and the ship, we worked out how much kinetic energy they have. We can now work out their power by dividing the kinetic energy, which is equal to the work done in reaching that speed, by the time it took them to reach that speed. So their power is equal to the kinetic energy gained divided by the time it took. So for the aeroplane, we've got power is equal to the work done in reaching that speed, which is going to be equal to the kinetic energy, 23,500,000, divided by the time, which is 56 seconds, and that 420,000 watts, and watt is the unit of power. For the ship, we have power is equal to 5 billion, 5 times 10 to the power of 9, divided by 900 seconds, which equals about 5.5 million or mega watts. So as you might guess, far more power. The ship requires far more power to actually propel it along at the speed that it needs to go than the aeroplane needs. Now we can work out our own personal power by doing work and seeing how long it takes us to do this work. So in this example here, a person is pulling a weight against friction through a distance. They're doing work against friction. In this example here, the person is climbing the stairs. They're working against the force of gravity, and they're moving through a vertical distance, which we can call height. Now in both of these cases, work done is force times distance moved, and power is work done over time taken. So we have power is force times distance divided by the time taken. In the second example, the force is equal to the weight of the person, and the distance moved is actually the height. So the weight of the person is mg, and the height is h. So in the second example, we could write that as mgh over t. In summary, kinetic energy, it's the energy of motion, and it's given by the equation kinetic energy equals half mv squared. It's easily converted to gravitational potential energy and vice versa. And power is the rate of transfer of energy. It's given by this equation. Power is equal to work done over time taken.